Oxidation states electron bookkeeping. Let's look at this reaction hidden up here in the corner. Carbon plus sulfur making carbon disulfide. What's being oxidized? What's being reduced? It's hard to tell, right? There's no oxygen involved. There's no ions involved. And that's the only way we've learned to identify that yet. So we came up with kind of a shorthand sort of a thing. It's completely a made-up device to help us figure out which is being oxidized and which is being reduced. And it's called oxidation states. They just help us to keep track of the electrons and where they're going. It's mostly useful in situations like this where we don't have any ions. And so how do we tell? So it's like bookkeeping for electrons. And what it does is it takes all the shared electrons and assigns them to the most electronegative element. Well, carbon and sulfur are very close in electronegativity. This is a covalent compound. The electrons are shared between them. And so oxidation numbers or oxidation states are a way of assigning those shared electrons to the more electronegative. It can get kind of complicated. But it's basically oxidation state and oxidation number mean the same thing. And they're just calculated based on the number of electrons that are assigned to each of the atoms. It's very important that we do not confuse oxidation state with ionic charge. It is not the same thing. We can assign oxidation states to the carbon and the sulfur. That does not mean that they have ionic charges in this compound. They do not. The easiest way to assign oxidation numbers is to follow this set of rules. And at first it looks a little bit overwhelming, and yet a lot of these things come down to common sense. And these rules, there's a hierarchy. Rule number 1 is more important than 2, which is more important than 3. Occasionally you might have 2 rules that seem to contradict each other. The lower number rule, closer to 1, wins if there's a conflict. So the first rule is that the oxidation state of an atom in a free element is 0. So if we have copper metal, we say the oxidation state is 0. It's not sharing electrons with anybody. So there's no shared electrons that could be given to the other element or that it might get from the other element. So if you have an element by itself, the oxidation state is 0. Same goes for chlorine. This is a diatomic molecule, but it's a single element. So elements are always 0. If you have an ion, a monatomic ion, the oxidation state is equal to the charge. So here we have calcium 2+ ion. It's a single atom as an ion, and so the charge is the same as the oxidation state. So that's +2 oxidation state. Chloride is -1. Third rule is that the sum of the oxidation states have to add up to 0 for a neutral molecule. They have to add up to the charge on the ion for a polyatomic ion. So here we have water. And so there are 2 hydrogen atoms. So if we take the oxidation state for hydrogen and multiply by 2 and add 1 times the oxidation state for oxygen, it has to add up to 0 because water is a neutral molecule. So the oxidation states have to add up to whatever charge is on that thing. For neutral molecules, it's 0. Here we have an ion, nitrate ion. Where did my pointer go? There it is. Nitrate ion. So here it has a negative charge. So overall, the oxidation states of those 2 elements, nitrogen and oxygen, have to add up to 0. So there's 1 nitrogen, it has an oxidation state. There's 3 oxygen atoms, they have an oxidation state. And so all of those have to add up to -1. In their compounds, group 1 metals have an oxidation state of +1. Group 2 metals have an oxidation state of +2. That may seem a little redundant because if we go back up here, the oxidation state of a monatomic ion is equal to its charge. But it's put in there, again, for a reason. In their compounds, the nonmetal oxidation states are assigned by looking at a table. It's on the next slide. Entries at the top of the table have priority over entries at the bottom. So we've got fluorine, hydrogen, and oxygen. Fluorine's -1, hydrogen's +2, oxygen is -2. Group 7s are -1, group 6s are -2, group 5s are -3. So these correspond to common charges on these ions, right? The group 5 nonmetals form anions with a -3 charge. But there's a hierarchy here. So fluorine wins. Fluorine is the most electronegative. Fluorine wins, and next we have hydrogen and oxygen. So if we have oxygen with fluorine together in a compound, fluorine gets his preferred oxidation state, and oxygen takes what's left. So if we have any rules that conflict, we take the higher list, the one that's higher on the list. So here in magnesium fluoride, the fluorine's going to have a -1 oxidation state. In water, the hydrogen gets +1. Oxygen gets -2. Here in carbon tetrachloride, the chlorine gets -1. In hydrogen sulfide, the sulfur gets -2. And in ammonia, the nitrogen gets -3. So let's do some examples. Assign an oxidation state to each atom in each substance. So the first one is just zinc. So what oxidation state do we assign that? 0. It's an element. Elements have oxidation states of 0 by themselves. Here we have copper 2 ion. It's going to have an oxidation state of +2 because that's the charge. It's a monatomic ion, and that's the charge on it. Now we have calcium chloride. So calcium is a group 2A metal, which means it forms a +2 charge, right? So if we break this into ions, we get calcium 2+ and 2 chloride ions. So the calcium has a +2 oxidation state. And what is the oxidation state of the chloride? -1. There are 2 chlorines. They each have an oxidation number of -1. So that's a total of -2. There's 1 calcium with a +2. It adds up to 0. It's a neutral compound. Does that make sense? Carbon tetrafluoride. Is this an ionic compound? No, it isn't. So then we have to think of that list of this list, right? So we start at the top and work our way down. So fluorine gets to be -1. So fluorine gets to be -1. Carbon doesn't show up on that list anywhere. How do we figure out what the oxidation state of carbon is? What do all the oxidation states have to add up to? 0. So we've got 4 of these guys, right? And 1 carbon. So we have a total of 4 negative in the oxidation numbers from fluorine, and the 1 carbon has to make up for all of it, so the carbon must be +4. So the carbon has an oxidation state of +4. This isn't any harder than sharing cookies or something. It's just weird. That's all it is. It's just weird. Here's nitrite ion. So here we have nitrogen and oxygen. And when we look at this list, fluorine, none of that. Hydrogen, nope. Oxygen. So oxygen wants to be -2. Fluorine is down here in group 5. Oxygen wins. Oxygen gets his way. Nitrogen has to take what's left. So we give oxygen its -2 oxidation number first. So this one is a little more complicated because there's a charge involved. So we've got 2 times the oxidation state for oxygen plus the oxidation state for nitrogen. There's only one of them. I'll call it X. And that has to add up to -1. So the X must be what? This is -4 plus X equals -1. So X must be +3. So the nitrogen has an oxidation state of +3. That's not what the table tells us nitrogen has. From that list, we would predict that nitrogen has a -3 oxidation number. But the table is set up to take into account differences in electronegativity and take some of the thinking out of it. And so oxygen gets the -2 and nitrogen gets what's left. In this case, it's +3. Any questions? Let's look at SO2. Sorry, SO3. So that list, it goes fluorine, hydrogen, oxygen, group 7A, group 6A, group 5A. So oxygen comes before sulfur in the list. Sulfur is in with the group 6A elements. So oxygen gets -2. So the oxygen is going to have a -2. There are 3 of those -2s plus X, that's the oxidation number for sulfur. There's only one sulfur. And these oxidation numbers have to add up to what? 0. This is a neutral molecule. There's no charge on it. So they have to add up to 0. So this is -6 plus X equals 0. So X must be what? +6. So here the sulfur has an oxidation number of +6. It's like playing a really weird game. Any questions? So let's go back to that equation that we couldn't readily identify what was being oxidized and what's being reduced. And let's assign oxidation states to the elements in this compound, in this equation. So here we have carbon. What's its oxidation state? 0. And sulfur. It's an element by itself. 0. And then we have carbon disulfide. So here we have a compound. And if we go through the list of rules, we get to rule number 5, which says for the nonmetals, you have to go look at that other list. Fluorine, hydrogen, oxygen, group 7A, still nothing. Group 6A. Sulfur's in group 6A. Those will take the same charge as the ions that they form. It's not an ion, but it takes that oxidation number. So that would be -2 for the sulfur. If we do a little math down here, we've got 2 sulfurs. They're each a -2 oxidation number, plus X for the carbon. There's only one of them, and that has to add up to what? Has to add up to 0. So we've got -4 plus X equals 0. X must be +4. So the carbon is a +4, the sulfur is a -2. Oxidation number. These numbers that we just assign to them. Now, can we identify what's being oxidized and what's being reduced? If we're going from an oxidation number of 0 to +4, it's oxidation. It's a loss of electrons. In terms of oxidation states, oxidation is an increase in the oxidation number. The oxidation number becomes more positive because electrons are being lost. We can't really pin it down, but this kind of virtual accounting system helps us to see what's going on. So the carbon is being oxidized, the sulfur is being reduced because its oxidation number is going down. So reduction is a reduction in oxidation number. Oxidation is an increase in oxidation number. Reduction is a reduction in oxidation number. Questions? We're going to do some examples. Use oxidation states to identify the element that's being oxidized and the element that is being reduced in the redox reaction. So the first thing we have to do is write the oxidation states for all of the elements. Each element gets its own oxidation state. So here we have tin. What's the oxidation state? 0. It's an element. Here we have nitric acid. Well, the order for the nonmetals was fluorine and then hydrogen. So hydrogen gets its choice, which was +1. So hydrogen gets to be +1. Next on the list was oxygen. So oxygen gets its choice, -2. And then we have to figure out what the nitrogen is. So we've got 1 hydrogen, and I'll put X in for the thing we're looking for. And there are 3 oxygens. So 3 times the oxidation state for the oxygen, and that has to add up to 0 because this is a neutral molecule. So we've got +1 plus X minus 6 equals 0. So we've got X minus 5 equals 0. So X must be +5. So for nitrogen, we've got a +5. Any questions about how I did that? So over here, we've got tin and oxygen. We do not have an ion all by itself. Tin is an ion, but we can't really tell what the charge is because it's one that has an unpredictable charge. So in that list of rules, I think it was rule number 4, it said that the group 1A metals always had +1 and the group 2A would be +2. And then it went on to nonmetals. So we're going to look at the oxygen first and use that to figure out what the charge is, or the oxidation number for the tin. So oxygen wants to be -2. So we have X for the oxidation number of tin plus 2 times the oxidation number for the oxygen, and that has to add up to 0. So X minus 4 equals 0. What's the oxidation number for tin? +4. Over here we have NO2, 2 nonmetals. The order is fluorine, hydrogen, oxygen. So oxygen gets to be -2. And what's the nitrogen going to be? The oxidation numbers for the two oxygens and the nitrogen have to add up to 0. We have the same situation. X plus 2 times minus 2 equals 0. So the nitrogen is also a plus 4. In a way, it's like pretending they have charges when they don't. How about water? Which comes first in the list, hydrogen or oxygen? Hydrogen. There's fluorine, hydrogen, oxygen. So hydrogen gets to be plus 1. So we have room over here, 2 times plus 1 plus X for the oxygen has to add up to 0. What's the X? Minus 2. Any questions about assigning the oxidation numbers? I'm going to get rid of this stuff. So now we have to get back to the question, which was identify the element that's being oxidized and the element that is being reduced. So we're looking for elements whose oxidation states change. Might as well start at the left. So here's tin. It had an oxidation state of 0, and over here it's a plus 4. That's an increase in oxidation number, right? So is that oxidation or reduction? It's oxidation. I'm going to say this is the one that's oxidized. Is the hydrogen changing? Here it's plus 1, and over here it's plus 1. Nothing happened to the hydrogen, right? How about the nitrogen? Went from plus 5 to plus 4. The oxidation number was reduced. A reduction in the oxidation number means that the element was being reduced. So the nitrogen was reduced. And the oxygen was minus 2, and it stayed minus 2, so nothing happened to that. You have to have one being oxidized and one being reduced. So you can think of it in terms of oxidation is increase in oxidation number, reduction is reduction in oxidation number, or you can think of these like charges going from 0 to plus 4. That would be a loss of electrons. Going from plus 5 to plus 4 over here, would be a gain. Reduction is gain, oil rig, reduction is gain of electrons. So who's the oxidizing agent? Yeah, the nitrogen. We actually say that the whole thing is the oxidizing agent, and then this would be the reducing agent. This would be reducing agent, and this would be oxidizing agent. Any questions? This is just kind of interesting. Hydrogen peroxide is an oxidizing agent, and it can be used to bleach hair. It can be used to bleach other things too. If you've ever used something like benzoyl peroxide, does the same thing to treat acne. You know that it'll mess up your towels and your sheets and your favorite shirt and anything that you get it on. It'll bleach the color out of things. Hydrogen peroxide bleaches hair by oxidizing the melanin in your hair, which is what gives it color. It also oxidizes some of the proteins in your hair that help to make your hair more slippery, and so if you bleach your hair, then your hair becomes more likely to tangle because it has a somewhat different texture. I'm not going to test you on that, but you might find it interesting.